Hello everyone. So today I am going to start the Smith chart basics. So if you are in second year or third year of your electronics and communication engineering BTech, you might have to study the transmission line and waveguide or transmission line and fields. In that, you have to understand what is Smith chart. So basically, if you solve any transmission line problems, in that you will have load, then line, and then you will find input impedance, VSWR, reflection coefficient, return loss, etc. using analytical method. So those analytical methods are, if I say there is a load which is given by 60 plus APJ ohm. It means that the load is having resistive part and the reactive part. And this plus sign shows us whether the load is inductive or capacitive. So here it is plus, that means it is inductive load. If it is minus, then it will be capacitive load. So this load, if you want to draw an equivalent circuit for this load, it will be consist of a resistor and an inductor. The corresponding value of this resistor and inductor you can find for given frequency. Now come back to the problem. If you have a load of 60 plus APJ ohm and line which is defined by 50 ohm, which is equal to 50 ohm, that is characteristic impedance of the line, and beta is given and length of the line is given. Then the analytical method to find reflection coefficient is, you can calculate ZL minus Z0 by ZL plus Z0. As you can see here, the ZL is a complex number, and after this calculation you will have a complex number. So you can say that this will be in the form of gamma x plus j gamma r plus j gamma I. R means real part, I for imaginary part. This can be also represented in terms of polar form as magnitude of gamma angle theta. So what we can observe here is, for every value of load, there is one reflection coefficient involved, and both, if this is complex number, this may be complex number, this will be also complex number. So in a Smith chart, we have two different planes. One is called gamma plane, that is reflection coefficient plane. Another plane is impedance plane. So these two planes are merged in a single chart to make the Smith chart. Similarly, to find input impedance using analytical method, we can apply the formula Zin equal to Z0 ZL plus J Z0 and beta L by Z0 plus J ZL and beta. This formula is valid for all type of lossless transmission line. So what we can see, the input impedance for every length of transmission line, for a given load, there will be an input impedance, which can be calculated using analytical method or Smith chart. So now we are going to start what is Smith chart. As I said, this will be the combination of two planes. One is gamma plane and impedance plane. So first of all, we will draw these two planes on the board, and then we will see how these two planes are merged together. So the gamma plane, axis of gamma plane is this, and this one is called center of Smith chart. This is center of Smith chart. as we know that the maximum value of reflection coefficient will be equal to 1. Maximum value of magnitude of reflection coefficient equal to 1. So this is 1, 0, and we can say that what is this axis? This is gamma r axis, and this axis is gamma I axis. Reflection coefficient real axis, reflection coefficient imaginary axis. And then we can make circle so that it will represent the maximum magnitude of the reflection coefficient. So maximum magnitude of reflection coefficient is 1. So if you take a circle, that means it is 1 at every point. The magnitude of reflection coefficient equal to under root gamma r square plus gamma I square, which represents a circle. So this circle means gamma equal to magnitude of gamma equal to 1. So our all the impedance will be inside this circle only. Outside this circle, you have reflection coefficient magnitude which is more than 1, or we can say that if magnitude of reflection coefficient is more than 1, that will become oscillator. So right now we are only discussing about the real load and the reflection coefficient. That's why the reflection coefficient will be always less than 1. So for the passive circuit, reflection coefficient is always less than 1. If it is active circuit, then magnitude of reflection coefficient may be more than 1. Okay, alright. This is gamma plane. Now we have to merge the impedance plane. So impedance plane, there will be this circle will represent the real part of impedance. So we have ZL impedance, which can be written as RL plus JXL. If you normalize it with the characteristic impedance, this will become RL by Z0 plus JXL by Z0. This RL by Z0 is small rl plus J small xl. This is normalized real part of impedance and normalized imaginary part of impedance. To represent these two on Smith chart, we have to know where is the impedance plane. So this outer circle, which is gamma equal to 1, represents R L equal to 0. We can say for general representation R equal to 0. RL is for only load representation, but since we are going to make impedance plane, so we can write in general R equal to 0. That is the outer circle. After that, all the circle will pass through this point, that is 1 0, the gamma 1 0 point. So all the circles, resistance circle will pass through 1 0. We can make the resistance circle like this, then like this, and so. So once you move towards the right of Smith chart from this point, the next circle will have higher value of resistance. So we can say this circle represents, let us say, R equal to 0.2, and this represents 0.4. Similarly, this will represent 0.8 in between. We have 0.4 and 0.8 in between, there will be 0.6. Okay, and finally this point, the center of Smith chart, where gamma was equal to 0, your R will be equal to 1. Okay, keep on moving towards the right side, the value will keep increasing. Maybe this is equal to 3, then 5, here we have 5, then 10, 20 and so on. So what we can see, the circle which is having the maximum radius is having the minimum value of resistance. The circle which is having the minimum value of radius is having the maximum value of resistance. So one of the axes of this Z plane is this one. This one is the axis. It's in circular form, not in the Cartesian form, but this circle represents r equal to 0. Now similarly, we have the reactive part. The reactive part is xi. So we can say the reactive part as x in general representation. We can say the reactive part is x, and that reactive part should be within this Smith chart, but those circles are on this line. So we'll consider only the part of circle which is inside this Smith chart. So suppose the circle is this one, we will not consider this portion, we'll consider up to this only. Then next, higher radius. So again we will not consider this portion, we'll consider up to this only, and so on. So as we are moving towards the left of Smith chart, the radius of these circles is keep increasing. So the smaller radius will have again higher value of reactance, larger radius will have smaller value of reactance. So the largest value is here. So you can say x equal to 0. I am going to erase this so that you will not confuse. So this is the smaller circle, then larger, 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 and if you keep on increasing the radius, the last circle will be a straight line. So that a straight line means the x equal to 0 here, and move towards this. This will be x equal to 0 0.1, 0 0.2, 0 0.3, 0 0.4, and finally at this point you have x equal to 1. This point is x equal to 1. Why? Because this point is crossing at 90 degrees. So this point is actually x equal to minus 1. X equal to 1. Then x equal to 2, 4, 5, 10, 50, 80, 100, and this finally the last point will be infinity. So you can see the r is also infinity. If you move from left to right, r is starting from 0, becoming 1, and then reaching infinite value. And then x is also starting from 0, increasing on this circle, and finally it is reaching infinite value. Similarly, this is the positive half of the Smith chart, or you can say these are the inductive loads. The load in this side will be represented as plus sign, and the reactive value below the real axis of reflection coefficient will have the negative value. So again we can find those values just by making these circles. Okay, so all the circles will be passing through this point, and we need to erase these portions which is outside the Smith chart, which is not of our interest. So if you make like this, keep on making like this, what will happen? You will get the negative reactance value. So it is 0, then minus 0.1, minus 0.2, minus 0.3, and so on. And whatever is cutting here, you will get x equal to minus 1. This is x equal to minus 1, minus 2, minus 5, minus 10, minus 50, minus 100, minus infinity. So this point is basically infinite point, also known as open circuit in. Why it is open circuit in? Because R as well as X both are infinite. So this is called open circuit in. And this side you can see R as well as X both are 0. So this is known as short circuit. Right? So basically the Smith chart is having the reflection coefficient axis and then impedance axis. So this is R equal to 0 and this is X equal to 0. So this is X equal to 0. So this is one axis and then X equal to 0 axis. Using this we can find if load is given, we can find reflection coefficient, VSWR, return loss, input impedance, etc. So next we are going to find the reflection coefficient, VSWR, input impedance, etc. So let us take a problem. Let's say ZL is 30 plus 40 J ohm and Z0 is 50. We are going to understand this using a problem. How to find reflection coefficient on a Smith chart using on a Smith chart and by calculating the length on a Smith chart. So there will be, let us say this is your Smith chart. This line you will not find on a Smith chart. So just I am drawing it so that you will have idea that this line is x equal to 0 line. On this line x equal to 0 as well as this line is also the real axis of reflection coefficient and this line is imaginary axis of reflection coefficient. Now you have to find this load that is equal to 30 plus 40. So first of all, as a first step, what we will do? We will normalize the load. So normalization means 30 plus 40 J ohm divided by 50. So how much it is? 0.6 plus 0.8 J. This plus sign shows that your point will be on upper half. 0.6 says that the resistance circle point, the point will be on resistance circle 0.6, and 0.8 says that the point will be on reactance circle 0.8. So first of all you have to find this 0.6 resistance circle, which will be given on a Smith chart. So let us say this point is 0.6. So the circuit, resistance circuit, which is passing through 0.6 here, will be considered as the resistance circuit for this point. So the point can be anywhere on this circuit. Now you will find the reactance circuit. So reactance circuit is 0.8. So it will be somewhere here. Obviously, the x equal to 0, x equal to 1. So 0 to 1 will be a spread on this line. X equal to 0, 0.1, 2, 3, 4, like that. And this is 0.8. So the intersection point of these two is this one, which represents the load point. Okay. Intersection of the resistance circuit and the reactance circuit will represent load point, and we have to find the reflection coefficient due to this load. What we will do? We will draw a line using a scale from the center of a Smith chart through this line to outside of the Smith chart, like this. So this line will cut at A to that point. The point is A, and B is the outer point of Smith chart. This is O. Measure the length of OA and OB. Measure the length of OA and OB and take the ratio. OA upon OB. This will give you the reflection coefficient magnitude. How will you calculate? Measure the distance from the center of the Smith chart to the load point, and then measure the distance from the center of the Smith chart to the outer circle where r equal to 0. So this is the OB and then OA, and take the ratio of OA and OB, you will get the reflection coefficient. Alright, now to calculate the angle of reflection coefficient, that is theta, this is theta equal to 0, theta equal to 90 degree. So the scale is given on the Smith chart: 0, 10, 20, 30, 45, 60, 75, 90 degree, and you can find what is the exact angle of this line, and then you can write that angle. So that angle is theta. You can calculate. It will be obviously more than 90 degree because the point is this side. So it will be more than 90 degree, less than 180 degree. So this is how you can calculate gamma, that is reflection coefficient, and the angle of reflection coefficient. Now next comes VSWR calculation. VSWR, it is also known as voltage standing wave ratio. So the basic definition of voltage standing wave ratio is, in a transmission line, if there will be standing wave due to reflection at the load, there will be maxima and minima generated in the transmission line. So the maximum voltage and minimum voltage ratio is called VSWR. I said maximum voltage and minimum voltage. So obviously the maximum voltage will be always more than the minimum voltage. That means the ratio will be always more than 1. So VSWR is V max upon V minimum, and we know that V max is always greater than V minimum. As per the definition, V max should be greater than V minimum. So the ratio of V max and V minimum will be always greater than 1, and it will never be negative. So the minimum value of VSWR is 1. Maximum value of VSWR can be infinity. When it will be infinity? If the V minimum is 0. If you have minimum voltage which is equal to 0, then VSWR will be infinity. So the range of VSWR is 1 to infinity. You have VSWR from 1 to infinity. And you can also find at this center R equal to 1, and at this point R equal to infinity. R equal to 1, R equal to infinity. I already told you, R equal to 0 here, X equal to 0, R equal to 0 here, here R equal to 1, and here R equal to infinity. So you can calculate VSWR by taking this OA arc from this center towards this. You can find that A point and read the value of R at that point, and you can calculate the VSWR. And this VSWR can be verified using the VSWR formula 1 plus mod gamma by 1 minus mod. Alright? So this is how you can calculate the reflection coefficient and VSWR. Next comes return loss. So return loss can be just calculated by taking the formula minus 20 log mod of reflection coefficient. Once you calculate the reflection coefficient magnitude from here, this magnitude, feed the value here and get the return loss. This will be in dB. So you get the value in dB. So I hope you understood how to calculate reflection coefficient by taking the ratio of OA and OB, VSWR by taking this arc OA and cutting on this line and reading the value of intersection point. So you will get VSWR. Obviously, on this line, it is from 1 to infinity. Do not intersect the point on this line because this doesn't represent VSWR scale. This represents VSWR scale as well as the resistance scale. So you can use this scale to find VSWR